Okay, so this lesson we're going to see the law of total probability in action, and it's going to help us understand a measurement technique that people use when they're trying to get their subjects to give honest answers to sensitive questions. Um, Questions about frown on attitudes. If you just ask somebody, "Are you a racist?" they'll probably say no. If you ask people if they've engaged in illegal behavior, they're also many of them are likely just not tell you the truth there. So this sort of broad problem is called social desirability bias, and a way of uh, combating that is the randomized response. Okay, so I'm going to go through an example of that is taken from a fairly recent UCLA PhD dissertation. Sarah Brierly, who's now an assistant professor at LSE, happened to give her practice job talk a couple days before we were talking about the law of total probability in 200A a couple of years ago. And I have her to thank for this good example. Um, so in her dissertation, which I guess more kind of good news for UCLA, which has recently come out in AJPS, great journal to be publishing in, she was interested in corruption. So the whole dissertation was about the correlates and consequences of corruption among bureaucrats in Africa in general, but in Ghana in particular is where she did most of her field work. And so, again, this thing of she's interviewing lots and lots of bureaucrats, and you just ask people, are you corrupt? They're probably not going to tell you the truth. And even something like, does your office do things that everybody knows are corrupt? Again, you worry about whether or not they're giving you the right answer or not giving you a truthful answer. So here's how she set things up. She gave the people she's interviewing a die, sort of a regular die like you'd play a game with, and a shield where like just a physical shield so they could roll the die and they could see how it came out, and she couldn't, and she knew, everybody knew that she couldn't there. And here's the instructions they were given. Okay, they were told, if your die rolled 1, answer this question about whether contracts are more likely to be awarded to political supporters. Answer that question yes, no matter what. If your die rolls a 6, answer no, no matter what. If your die rolls a 2, 3, 4, or 5, then answer the truth. Okay, so the undesirable response here would be yes. Okay, yes, we're giving them to the contractors who are our big supporters, not to the contractors who have the best bid. But that yes answer could just be because of the way the die came up, or it could be because it's true. But so the randomization gives the subject some cover that might allow them to be more comfortable admitting to something they wouldn't otherwise admit to. So let's see, like if that actually can give us the number that we're interested in, and I'll take you through the steps of that. Okay, so we're going to assume that we've got some respondents here and that they have followed the instructions here. Okay, so we're going to assume that yes, everybody who rolled a 1 just answered yes, no matter what. They rolled a 6, they just answered no, no matter what. They just, if they rolled 2 through 5, they gave the truthful answer. Okay, so let's set up a probability model for this. So the thing that we observe is Y. This is the event that the respondent answers yes. Answers yes to the question. That's what we're entering in our spreadsheet there. And let's assume for this example that the probability of a yes answer in this data was 0.4. Okay, so 40% of the people interviewed said yes here. What are the other events? Okay, so the other events are D1, D2 through 5 is one event, and D6. Okay, so this is the outcomes of the dice. Okay, the die rolls a 1, die comes up 2 through 5, or the die rolls a 6. So set of events, it's looking like kind of an LTP type problem. Let's write Y, partitioning it in terms of the dice rolls. Okay, so one way we could get a yes answer is that we could get a yes answer conditional on D1. And how likely is that? That's the probability of D1. And another way we can get a yes answer is yes conditional on D2 through 5. And that happens with probability of D2 through 5 plus probability of a yes answer conditional on D6 times the probability of D6. That's our law of total probability right here. So just emphasize LTP formulation. Okay, so in the last lesson, and often we use the law of total probability to actually find the total probability, but we don't have to use it that way. In this case, we know the total probability. What we're actually interested in is what is the probability that somebody who is in the 2 through 5 outcome said yes? What is the probability that somebody who was told to answer truthfully said yes? Okay, so this is what we want to know. Again, just sort of let me emphasize, the research design gives you this probability, the people who said yes for reasons that are deliberately obscured to give them some sense of anonymity. But what we want to know is the set of people who answered truthfully. Okay, let me say that more carefully. The set of people who answered yes when they were in the condition that told them to answer truthfully. We've got all the numbers that we need to calculate this. Okay, so let's just put in the values here. So the probability of Y, well, we said that's the data that we collected. That would be the results here. So that's 0.4. What's the probability of Y given that our die rolled a 1? Well, we're assuming that the people followed the instructions, so that is 1. Okay, everybody whose die came up 1 was supposed to say yes with probability 1. And what is the probability that we're in that condition? It's 1/6. It's a fair die. Okay. The probability of a yes answer given that we're in this condition where we're answering truthfully, that's the thing we're trying to find. So we're leaving that as a variable. But what's the probability that we're in that condition? Okay, well, it's 4 out of the 6 possible equally likely outcomes. So 4 or 6 or 2/3. So probability that we're in the truthful revelation condition is 2/3. What is the probability that they answered yes, given that the die came up 6? That would be 0 for following the instructions. Okay. That happens with probability 1/6. So it's making sure we're setting everything up correctly. We've got the 3 probabilities. We're taking a weighted average, and these weights should always sum to 1. Okay. The divide and conquer strategy behind the law of total probability depends on a partition, and so the probabilities of these partitioning events better sum to 1. Yeah. So, and it does 1/6 plus 2/3 plus 1/6 sums to 1. Yeah. And that's really all we need. Now it's just a matter of a little bit of algebra here. So I don't have very much space here. I'll leave you guys to check my calculations, but this rearranges to the probability of y conditional on D2 through 5 being equal to 0.349. And that is the estimate of the fraction of respondents reporting corruption. So pretty cool. And all it took was the law of total probability.